Now let's see the operations on singly linked list. If you list out the operations, inserting a new node, at end, insert middle, insert at begin, delete a node, search for a node, display the data. So these are the different operations we can perform on singly linked list. Now we'll see the implementation of singly linked list. Let us write the code for inserting a new node at the end of the list, insert a new node in the middle of the list, inserting a new node at the beginning, deletion and search, and display the data of the singly linked list. Let us start with an example. By considering a singly linked list like this, for this we have to define a start pointer and we have to define a structure for the node, and every node will have data part and link part, and this will be your last node with link part equal to null. And every time when you are inserting a new node, that new node we can take it as an end node, and while performing the operations we have to consider a temporary node, a previous node, like that. So now let's take the structure defined for a node. Struct node. Node is having this data part. Let us consider some integer value, something like 20 is inserted here, 30 and 40 is inserted here. So the first part is declared as integer and it is the name of the field. First field is defined as data, and the second field is, as we know, it is the address of the second node. So second address of the second node, for that particular addressed referred data, it is a node type data and which is defined as struct type. So that address field should be declared as of that node type. So it comes struct node star link. This is the structure. Then for the start pointer, initially when there are no nodes in the list, we have to consider the first link is referred to start, which is null. So it can be defined as struct node star start, which should be defined with null, which indicates that there are no nodes in the list. It is the initial situation. And the pointer is defined with start. Now what we do is that let us define a new node, struct node star, that new node can be declared as n, and let us declare a temporary node also, and let us declare another pointer, previous pointer. Now we have to allocate memory for this new node. So it is n equal to, that new node is of type struct node as per the syntax of your malloc function. To allocate memory, this is size of struct node type. So what happened is, n has got its memory for its particular node with two fields, data field and link field. And now moving on to insert at the end. So let us define that. Indent function, insert at the end with a data value let's take this value read inside the function. So in end, let us declare this item, we can read it. The value we got, and we have defined our n node, and n's data is this item, and n's link is null, and here this start pointer is a global pointer, so throughout all the modules it works. Now we don't have any elements in the list. Now this n is the node, first we have to insert into the list. So assume that this item value is 20 and we have only the start pointer in our list. Now we got this n with 20. We have to insert this n into the list. For that, initially, let us implement this initial node insertion in end method only. So it is if considering the list is empty, if start is null, so it is the case no elements in the list. Then what we have to do is that we have to make this n node as the start node. So our start node will get the data of n, and start link equal to null. So combining these two, integrating these two, what we have got is, now our start is referring to this n node with null pointer. First node is inserted. Here the statement indicates start equal to n. The start is a pointer variable, address variable, which is taking the address of n node. N node's address the start has taken. So using start, you are going to refer this first node. Else case is that it is not the first node, it is the second node. If now here the situation is, this is the status of the list. Now a new n node we have received to insert with, n is 30. So now for this start node we have to insert this new node n. So where we can insert n? So for the start node's link pointer should refer to our end node. So in the else part, we'll get the instructions, and for inserting this new node n, we have to traverse our list from the start to till the end of the list. If this is the end, if this, like our method is inserting a new node at the end, so till the end of the list we have to traverse it. So for traversing that, let us take this temporary variable temp equal to start. So temp starts from the first node, while temp's link is not equal to null. You have to traverse. Temp link is not equal to null. You have to go to the next node. How do you go to the next node? It is by making temp equal to temp link. This is your temp link. This is your current temp node. By making temp equal to temp link means it is the address of the next node. By doing that, this will become your latest temp. So here the traversing is that temp equal to temp link. So by doing this traversing, you will be accessing starts from the start node till the last node where the temp link is equal to null. For the last node we have already made the link part as null, so till the last node it traverses it. So at the end of this while loop, we will find the last node as last node can be accessed with temp. So for the temp we have to add our new node now. So now this is our last node and this is our end node to be this is our temp node and this is our new node to be linked to this. So here to connect these two nodes, how we are getting the things? So this temp's link equal to n. Temp's link is should be connected to n, so it is temp link equal to n, and n's link should be made null. So with this we could make this and this will be our null. So this is how you can do insert at the end. For this the priority operation is traversing the list from start to the last node. The key for this key operation, the code is temp equal to temp link. Let's continue with the second module. In insert at the begin. We have our end node with data 50, and this node we have to insert into this list and insert begin. So this node to be inserted at the begin of the linked list. So what should happen is, after inserting this node before this first node, this has to become our start node, and the link of this, the pointer of this node should refer to the currently first node of the linked list. This is what we have to do. But before performing insertion, first of all we have to see whether the list is empty or not. Actually, in end, insert end, we have handled if the list given is empty, making the end node as the begin node. So there, as we have handled that, here we are in only through one insertion operation we are going to start with the first node insertion. In the other two insertion operations, insert begin and insert middle, if the linked list is null, we are going to give a message saying that list is empty. There is no possibility to insert the new node. The first node to be inserted should be done through in and only. Okay. Now in begin, if in order to check whether the link is list is empty, if start is null, we are going to give a message that list is empty, no possibility to insert a node. Okay. In the else part, now we are going to see the actual insertion. And the actual insertion, through start we can access the first node. So it can happen like n nodes link equal to your start, and your new start will be your n node. Here two things, n link should refer to this first node, so n link equal to start. Start is having the address of the first node, so we are equalizing into n link, we are storing the address of this first node, and then this node has come before this start. Here it has come. Your n and link is stored with the address of the first thing. And here you have your start pointer. This start pointer, now it has to refer to your n because n has become the first node. For that, what we have to do is address of n node we have to store in the pointer start. So it can happen through start equal to n. With this we could do insert begin. This should be closed here. Okay. Now we'll see insert middle, which is more complex operation than insert end and insert begin. Let's first discuss that and then write the code. For this particular case only, it is that here is your stack pointer and this is your list width. Let us take 4 nodes. Now it is required to insert an n node with 100 data. In between this node with 30 data and node with 40 data. In between these two things you have to insert. It is insert middle. And it is our n. We have our n. We can read an item and into n data we are keeping that item. And data here is what we have taken is 100. Now here if you see, to insert this new node in between 30 and 40, actually the address of 40 node is stored in 30 address location. Address of this particular node is stored in this node. Now after inserting this, address of n should be stored to 30 and this link part of 100 needs to have the address of this next node 40. So here two steps we have to perform. Ends link should hold the address of this new node. For this, what we have to do is, wherever we have to insert this new node, till that node position we have to traverse this list. Traversing. For traversing that, what we'll do is, we'll take the first node as our temp node. So this is made as our temp node. I will make the temp node temp equal to start. So this is our temp node now. And we have to check where is our node 30. After 30, in between 30 and 40 we have to insert. So here, before this only, we are read node data, temporary node data, which is 30. So we have to traverse while temp data is not equal to this 30. We have to traverse our list. First temp is this. Is temp data is 30? No, this is not temp data. So we have to move to the next node. How to move to the next node? It is by making temp equal to temp link. You can move to the next node. Now after executing that, this will be your temp. Now temp data, if you observe, it is equal to 30. So you have reached your locations. Like this you have to traverse. So with this, we got this node is named as temp and this is our new node. Now we could identify after which node we are going to insert it. So it is temps link. Temps link we have to put in N node. Into N link. N link, we can keep the address which is stored in temp link. Into N link, we have to keep temps link. It is the address of the next node. And into temp link, we have to store the address of N. With these two steps, we can connect this N node in between temp and the next node. Here actually these two steps should not be change their order, because if you do this temp link equal to N first, we will be losing the address of the next node. For that, what we have to do is, first of all, this temp link which is referring to the next node, that address we have to store in this new node's link part. That we could do with N link equal to temps link. Then the address of this N node we can put into temp link. It is temp link equal to N. With these two instructions, we could insert the data here. So here we can close this. This is our insert middle. Thank you. Let us see the different cases involved in deleting a node from single linked list. So here the possibilities are, if you consider this particular single linked list with 5 nodes, delete a node. The node to be deleted may be the first node. You can delete one case, and it may be the last node. It is another case, or it may be the middle node. These are the three possible cases. And here one more new thing to follow is that after deleting a node, the memory whatever is allocated for that particular node, you have to free it using your free function of memory allocation. So it is free of start or the node, address of the node you should mention as a pointer for that free function. Okay, so now to start with, delete the first node. First node, start node to be deleted, this node to be freed. So once you delete this particular node, next node of the start should become your start node. So from one node to another node to traverse, it is very simple through your start equal to start link, which is storing the address of start link. Start link means this particular address. In this link part, what is the address you have? You have the address of the next node. Next node address, if you store in your start pointer, it indicates that leaving this current node, you can move to the next node. Okay, so through this you can go to the next node actually, but we have to free the memory of this particular first node, which is accessed through your start pointer. But here you are modifying you are going to modify your start pointer. For that reason, what we have to do is we have to create a temporary pointer. So it can be your struct node star temporary pointer is created for your structure. Now what we can do is that you can make temp equal to start. So the address of your start pointer you are storing in temp pointer. Then you can simply make start equal to start link. With this start equal to start link, your new start pointer is referring to the next node. Now we have to free this node. This particular node now it is referred with your temp pointer. So you can write it free of temp. But here one more case we have to consider. We have to check whether your list is empty or not. For that, as usual procedure, you have to check your start as null or not. If it is null, you have to say that list is empty, else you have to go for this particular procedure. This is for delete the first node. Consider the situation delete last node. If you need to delete this last node, it is clearly showing that from the start pointer, from the first node, you have to traverse till the last node. How can you identify the last node? Last node's link part, it will always have a null. So you have to traverse this list from the first node till the last node. While traversing, you have to see that the previous node of this last node, now its address to be made as null because the next node of this particular node is going to be deleted. So we have to see that this particular node also should be referred or should be defined with a new pointer like previous and we can delete the next one. We have to store this particular pointer. So for this delete last, you can simply check start is null, list is empty, else you have to traverse your list. For traversing, you have to take your temporary pointer and temp equal to start, and using a loop only you can traverse, because we don't know how many nodes are there. From the first node to last node we have to traverse, while this temp link is not equal to null. Not equal to null, you have to traverse. You have to make temp equal to temp link. So first the temp is your start and temp link is not equal to null. So with this statement you will go for the next node. Now this will become your current temp. But before making this as your current temp, you have to name this before node of this as previous. So here, before making the next node as your temp node, its previous node you have to store in previous pointer. So for that what we can do is temp link will be the next node, means temp will be the previous node. So previous equal to temp. With these two statements, once the complete list is traversed, in temp pointer you will be having this last node. This will be referred as your temp because it continues, this loop continues till its link is null. So once the temp comes here, it stops this loop and it comes out. So this will be your temp and this will be your previous. So once having these two things, now what to delete? This last node to be deleted. For that, you can simply make your previous link now should be made as null, because this has to be now onwards treated as the last node. And now our last node to be freed. How to access the last node, which is named with temp. So it is free of temp. So this is how you can write the code for delete last. And we have the other module, delete middle. So this is your delete middle node. If this is the node to be deleted, which node we are going to delete? We need to identify based on its data value. So its data value is 30. We are saying that node to be deleted. Now what should happen after deletion? The link of this previous node of this 30 has to be linked to the next node of 30. So now if you traverse the list from the start to this particular node, and if you can name this node as your temp node, and if you can make this before node of temp as previous, then this previous node's link should be modified with your temp's link. With that single statement, we can delete this particular temp node. But in order to identify this node as your previous node and that node to be deleted as temp node, you have to traverse your list. So it is you can read here the node data to be deleted. Enter the node data to be deleted. It is, you are reading here, its information is 30 and this is our list what we have taken. Now you can check whether the list is empty or not. Your start is null. If it is null, you can say that deletion is not possible, else it is our case. Now we have to traverse our list from the start node to that particular node. For that, what we can do, we have to take a temporary temp pointer which is assigned with the address of the first node at start, and we have to traverse our list now while temp data is not equal to this particular information 30. So it is not equal to that information. For traversing, we are using the same statement, temp equal to temp link. But before doing this, temp equal to temp link incrementation, we'll be defining the previous pointer with the particular temp. So with these two statements, we can identify this as the previous pointer and this particular temp is the current pointer. So once those two have been identified, we need to delete this particular thing, this particular node. Now, for linking the previous node of this temp and the next node of this temp, next node of this temp is accessed using temp link. So we can link our previous nodes link is equal to temp nodes link. It's the single statement. It can be connected. Now we have to make the temp node free. So using our free function, free of temp. So using this code, we can do the deletion of a node using your middle. Now let's see the display. What is the purpose of this display is, we want to display the data which is stored in the list of nodes or in the singly linked list. First node the data is 10, second node 20, third node 30, fourth node 40, fifth node 50. For this, in order to display the data which is stored in the singly linked list, we need to traverse the singly linked list from the first node to till the last node whose link part is having null, and in each iteration we have to display its data value. So for that, display code we can define the same thing. If start is null, printf list is empty, there is no data to display, else our same procedure of traversing the list. It is your temp pointer, temp equal to start, and for traversing the whole list, while temp link is not equal to null. Now currently this is our temp. So our temp data we have to display. So for displaying, we can use our printf statement, printf, and to be displayed is your temps data. After displaying this particular node's data, you have to move to the next node. How do you move to the next node? By making temp equal to temp link. So this happens for all the nodes, but when the traversing reaches to this last node, as last node's link is having null, control comes out from this while only. It will not display the value of the last node. For that we have to write again another printf statement. Once this loop is finished, control comes. That time your temp refers to the last node. So by writing this printf statement, temp data, the last node's data also gets displayed. And for this particular code, you can see the output. Data displayed as 10, 20, 30, 40, 50. This is the output for the display function. Thank you. Now let us see one application of singly linked list. That is to store polynomials information in system's memory. To store the polynomial information in system memory effectively, singly linked list we can use. First, if you see, taking a polynomial example, 6x power 4, 5x square, 6x plus 7. If you consider this polynomial information, in a polynomial corresponding to every term will have its coefficient and will have power of x. These two informations we have to store. So if you go for array representation for this, array representation already we know that indexes are fixed 0, 1, 2, 3, 4 like this. Here this index values we can use for representing the powers of x. So here we have x power 4 term, till x power 4 term we have. So we'll get an array with size 5. Now to store this first term information, it is x power 4. So it is with the 4th index, 6 will come here, and with 3 power there is no element, so there is no coefficient. The coefficient of it is 0, and with 2 it is 5, with 1 it is 6, with 0 it is x power 0 term, it is 7. Like this it is represented. So here one point we can observe in the polynomial, how many x power terms are there. Like in the sequence, we have to consider x power 0th term to the highest x power term. In between, how many different values are there, that much size array you have to consider. So like this, wherever even the term is not there, you will be having one location to store the value as 0. So here assume, take the case even this 5x square is also not there. Then this particular term location will be there created only, but this value will be 0. So here if you see the effective uses of this particular array, actually we have only 3 values to be stored, 7, 6 and 6, but the memory is allocated for 5 elements. This is not effective method for representing polynomials, for storing polynomial information in the memory, because it's costing more unnecessarily. The same thing if you try to represent using your single linked list. Here how many terms are there? 3 terms are there in the polynomial. So we need to have 3 nodes in the single linked list. But in every node, what are the things to be stored as? One is coefficient, another one is power of x. And here as following your node structure, our node will have data fields and link fields. Here how many data fields are there? 2 data values are there. So for 2 data values, 2 locations we have to give, and the third location is for link or to store the address of the next node. So this is our node structure for our polynomial. And how many terms are there? That many nodes we need to have. So it is that this will be our first node, and which will hold the address of the next node, and we have the third node like this. And the first node, assume that it is x power 4th term node. First coefficient, then the power, then the address. Next term it is coefficient is 6 and x power is 1 and the address. And for 7, coefficient is 7, x power, 0th term it is x power 0, and the address of the last node, the link part of the last node, will hold null value in the list. So here if you see this particular storage representation or storage method for polynomials, the single linked list, it's giving us an effective or cost reduction method.